All right, Colts, welcome back. We're going to do section 2.1 notes, conjectures, and counterexamples. So our objective for this section of notes, starting unit 2, when we talk about proofs, is we're going to be able to write and analyze conjectures by using inductive reasoning. And we're going to be able to disprove conjectures by using counterexamples. So these are some of the definitions they had from the book. I'm also going to just put a little bit more specifics, and then I'm going to have a PowerPoint online. But the first word we're going to talk about is going to be inductive reasoning. Okay, so inductive reasoning, it says reasoning that uses information from different examples to form a conclusion or a statement called a conjecture. Okay, the biggest thing I want you to know is that you use specific examples and an observed pattern to reach a conclusion. Okay, so in our textbook, it talks about how it never snows in Florida. Okay, one of the students says, it never snows in Florida because she's never seen any snow. So that could be a conjecture that she is trying to prove or trying to say based off of this pattern. Okay, so that word, inductive reasoning, based off of patterns, okay, that we have observed. So that word conjecture, it says it's a conclusion of a statement, but I want you just to make sure we put it on there. It's a conclusion of a statement that is reached. So let's get rid of that period. Reached when using inductive reasoning. Okay, that's that word conjecture. So you see a pattern, you guys, in a way you make an assumption or a hypothesis. In this case, we're going to call that statement a conjecture. Okay? And then, but sometimes someone might say, well, I've lived in Florida before and I saw that it did snow one time in 2016. And so we would call that a counterexample. Okay? Counterexamples are a false example that proves a situation not to be true. So I don't really like that definition very much, so I'm going to say it is an example that shows the conjecture to be false. Okay, and there's quite a few different ways you could do it. It could be a number, it could be a drawing, or it could be a statement, just to give you a few examples. So those are our 3 vocab words for this section. So we're just going to try a couple of examples. So example 1 is we're going to say, all right, we're going to write a conjecture about the next number in this sequence. So I'm going to write it down here so we have a little bit more space to work. So I have 1, 3, 9, 27, and 81. And I want to know what that next number would be. Okay? So first off, we have to find the pattern. So if I go from 1 to 3, there's a couple possibilities. You could say that I add 2, but if I go to add 2 to this next one, we see that it doesn't work. Okay, 3 plus 2 is going to give us 5. So I want to see if there's a pattern that's the same for all of them. So instead of adding 2, we could say that we multiply by 3. 1 times 3 is going to give us 3. 3 times 3, I'm going to use a little x instead, make it a little easier. 3 times 3 gives us 9. 9 times 3 gives us 27. 27 times 3 gives us 81. Okay, so we see that our pattern is that each number of the sequence is 3 times the previous. Okay, or you could say each one's multiplied by 3. So it's saying write a conjecture. So our conjecture, we're going to say is we're going to say the next number in the sequence, is that how you spell sequence? Will be 81 times 3. Okay, and when we do 81 times 3, we end up with 243. So here we can write 243. Okay, so that's one example of writing a conjecture. So we're going to go down here where we have one where we have a diagram. It's a little bit different. So it's saying, write a conjecture about the number of squares in the next figure. All right, let's do red. So first one, we're going to have 1. Second figure, we have 4. So we have, and then the next figure, we're going to say we have 9. So we can see how many we have total, but let's count how many squares we have on the sides. So sometimes you just have to go at it with a different perspective. So here I have 1 on this side. 1 times 1 is 1. Here I have 2 squares and 2 squares. Here I have 3 squares and then 3 squares. Okay? So we say, all right, we look at our pattern and we say that the sides increase by 1 each time and are multiplied. Something like that. Something if you can just tell me and explain it. So if we were to do our next one, let's see if Ms. Chandler can draw a square. We would say that this one has 4 on either side. Right? So I would say I have 4 here and I have 4 here. Therefore, it would give me a total of 16. So our conjecture for this one is that we would say the next figure would have 16 small squares and the sides would be 4 by 4. Now some of you might have wrote 4 by 4 first, that's fine. Okay, so that's an example we're using with our diagrams. Okay, let's go to number 3. All right, number 3, we're going to say, all right, what do we know? What can we assume? Or what can we see from the pattern? Maybe not assume. Assume is not a good word in geometry. So I know that angle 1 and angle 2 together form a right angle. Okay, so if we remember, right angles are 90 degrees. So if we remember from our definitions, what is the word that we use when angles add up to 90 degrees? So I'm going to say angle 1 and angle 2 are complementary angles. That's the word. Okay? So we got to make sure we know that when we're talking about right angles, we can go a couple different ways. We can go to the 90-degree way, or we can go complementary, depending on what the question or the proof is going to need. So right angle kind of bridges between those things. All right, let's go down to number 4. Number 4, okay, let's draw a picture to help us out. We're going to say, all right, I have angles ABC and angle DBE, and they are vertical angles. So I'm going to draw some lines. Okay, and I know I have angle ABC. So let's label this one A, B, and C. And if you notice, you see both of them have B in the middle. So that's one of my angles here. Now if they're vertical angles, my other angle better be here. Okay, so I need D, B, E. So I don't care which side you put the D or the E on. It doesn't matter technically. You can have a D here, B is still going to be the centerpiece, and then E. So now we say, okay, I have these 2 angles, and they are vertical angles. I can also conclude that these angles are congruent because they're also vertical angles, even though it's not telling us about that. So if we remember from our definitions, and I kind of said that as we were talking about it, if two angles are vertical angles, okay, then we can say that those two angles are congruent. So I can say angle ABC is congruent to angle DBE. So if two angles are vertical angles, then they are congruent. And that's one of our definitions. So I believe it's number 13 on our definition list. Oh, number 12, excuse me. If two angles are vertical angles, then they are congruent. So that's what we used. So if two angles are vertical angles, then they are congruent. That would be our reason if we were talking about a proof in this case. Okay? All right, let's go to our next one. All right, so for these next ones, we're just going to determine if the conjecture is true or false. And if we think it's false, we have to give a counterexample for any false conjecture. All right, so here we go. Number 5. If AB, let's use another color, AB is congruent to BC, so we see that they're both 3 centimeters, then B is the midpoint of AC. And B is the midpoint of AC. Okay. If you remember from our definition says if A, then B, then C, and AB is congruent to BC, then B is the midpoint of AC. This terminology right here, okay, is saying that they are collinear. Okay, they are collinear. So in our case here, they are the same length, but they are not technically on the same line. It's 2 different segments. Okay, so in this case, we're going to say that this conjecture, let's use a different color, is false. Point B is not on a segment AC. Okay, so it is not a midpoint. Okay, these right here are 2 separate segments that share point B. So our counterexample for this is going to be using our definition. We'll write it under here, our counterexample. Okay, is if we had that definition, and we're saying that we have A, then B, then C. Okay, we're going to draw a segment, and we're going to say, all right, I have this segment here. I'm going to label this one A, I'm going to label this one C, and it's telling me that B is there. If I know that A, B, and C are collinear, and that AB is congruent to BC, then I can conclude that B is the midpoint of AC. They have to be on the same line, though. Okay, let's go to number 6. So number 6, if A, B, and C are collinear, okay, so if you remember from this, it means that they are on the same line. Okay, then it's saying that AB plus BC equals AC. Okay, so it's saying if they are on the same line, right, we can even say AB is this piece here, BC is this piece here, equals AC, right? But did it tell us that it was A, then B, then C? It did not. It just told us that they are on the same line. So I'm going to say that this is false, and I'm going to give you a counterexample. What if I had the line and it was like this? and I had C here. All three of those points are on the same line, but this would be AC plus CB, excuse me, equals AB. So we would say, though they are all on the same line, point C could be between A and B, resulting in AC plus CB equals AB. Okay, so sometimes they're tricky. Sometimes you're like, oh, that'll work, but we got to make sure. Because a lot of times when they do a conjecture, they're saying that's the case. That's always the case. We want to make sure. Because if not, if we can prove it with a counterexample, we want to make sure we have that counterexample. All right, we're almost done. Number 7. All right, if R and S are supplementary. So we need to remember from this word supplementary, what does it mean when words are supplementary? Or excuse me, angles are supplementary. What does that word supplementary mean? It means that they are gonna add up to 180 degrees. Okay, so kind of like how we had right angles, we have this word supplementary, and we can go a couple different ways. Sometimes we can go and we can say that they are a linear pair if we have a picture, and we can also conclude that they are 180 degrees. We need those. We can't just go from linear pair and just assume 180 degrees. You have to go linear pair, I know they're supplementary, and then they're 180 degrees. Okay? So if I know that R and S are supplementary, that means I know that angle R plus angle S equals 180 degrees. Okay? And then it says that angles R and T are also supplementary. Angle R plus angle T also equals 180 degrees. I'm going to kind of give us some space away from that one. Okay, so just from that, angle R and S are supplementary, and angle R and T are supplementary. And then it's telling us that angles S and T are congruent. So it's almost like a process of substitution that we have here. If we see right here, okay, if I were to go through and I were to substitute and I were to go through and solve, I could see that angle S is going to be congruent to angle T. And if you're not sure, you could also pick a number for angle R. So let's try that, okay? So maybe we say they're supplementary. That does not necessarily mean that they are a linear pair, though. So say I have angle R right here. Okay, angle R, we're going to say, is 120 degrees. So if angle R is 120 degrees, then my angle S is supplementary to it. And I'm going to say, all right, what does angle S have to be in order to have it equal 180? It would have to be 60 degrees. Okay, so I would also say, all right, angle R again is 120. What does angle T have to be in order for it to equal 180? It would also have to be 60 degrees. So therefore, we can conclude that angle S is congruent to angle T. And so we'll say that this conjecture is true. All right, last two. Here we go. If angle ABC and angle DEF are supplementary, so we got that word again, supplementary, right? So it means they're going to add to 180. Then ABC and DEF form a linear pair. Okay? So remember, linear pair, in case we forgot, it's when I have opposite rays, right? So there's my opposite rays. We'll label this A, we'll label this B, we'll label this C. We'll call this one D. That means I have an angle here and an angle here, and they are a linear pair because they are opposite rays and they also add to 180. Okay, so angle ABC, so let me label it actually, so where it matches our letters. ABC and angle, oh, it's not going to work either way. Angle ABC. So if I have angle ABC and DEF, just because I say they're supplementary does not necessarily mean they're a linear pair. So if you remember from our definitions when we did them, I could say that I have angle A, B, C, and it could be 75 degrees. And then over here, I could say that I have angle D, E, F, and it would be 105 degrees. So those angles are still both supplementary, but they are not a linear pair. They both add up to 180, but they are not a linear pair. Okay, so we're going to put that here. So we're going to say false. Let's use a different color. The angles could be non-adjacent. Remember, not next to each other. So this is our counterexample. So they are not a linear pair, but still supplementary. Okay, so make sure you don't jump to conclusions too fast when we're doing these proofs and different things. All right, last one. I apologize, this was just our perpendicular symbol. And then Microsoft Word didn't like it super well, so it gave us that blue. But so this is telling us that these two segments are perpendicular. Okay, so if I have segment, well, let's do without the line. Segment DE is perpendicular to segment EF. Because I said that they're perpendicular, okay, it's telling me that angle DEF is a right angle. So if we remember from our definitions, if two lines are perpendicular, then they intersect to form a right angle. Okay, so DE and EF are segments on these lines, or rays DE and rays EF. Because I know that they are perpendicular and that was given to us, angle DEF is a right angle. That is true. That is what we conclude from them being perpendicular. And this concludes our 2.1 notes.